Previously, we looked at one example on the spring system. Now we look into principle of work and energy. So let's say you have a mass, a particle with a mass moving in the curvature of collinear motion. And this object here, or particles here, was subject to the external force. Meaning there's a force when this particle moving in the collinear motion, there's one particular force pulling this particle in the certain direction. In this case, we give the pulling force or external force by resultant force Fr here, which is equal to all the force acting on the object. And you know that every time we have a curvilinear motion or object that move in the curve, we will always automatically, we will have normal axis and tangent axis. Okay, we have come to chapter 3 already. So by automatic, next time you see a curvilinear motion or there's a curved motion, automatic build the axis for the particles. Normal always pointing to the center of the curve. Tangent always follow the direction of the particle. The particle move from here to here, so tangent is this direction. Okay. Now we try to move, derive the equation of motion in the tangent direction. Okay, in a tangent direction. Why we do not interested in normal? Because if you talk about work, force and displacement must be in same direction. But if your force is 90 degree, it do not generate work. Okay, but after 90 degree, it generate negative work. Okay, so have that concept. Now we look at tangent direction. So we write the equation of motion, F equal to ma, but use the sub t to represent in the tangent direction. I think you're familiar with this one. On the left hand side, you look at the force. On the right hand side, you look at the acceleration. Or when you build and you want to use the equation of motion, you always see two diagram, free body diagram and kinetic diagram. Free body diagram settle the left hand side, kinetic settle the right hand side. Okay. You know that now you need to pull or recall one of the equation we learned in chapter 1 when we derive the ST graph to VT graph to AT graph. There's one equation of Newton that we derive A equal to V dV ds, or there's one equation A ds equal to V dV. Okay, A ds equal to V dV. This one you can find in chapter 1 when we derive the ST graph to VT to AT graph. Okay, now we apply the acceleration equation here. A equal to V dV over ds. Okay. And every time you have a integration, right? You know that every time you have a d something one side, d something one side, the next step always we look at integration. So when you integrate, okay, when you integrate both sides, you will get f ds and mv dv. Okay, or you pull your ds, you pull your ds over here, you integrate. Okay, you integrate. Okay. Okay. Okay, before we come to this one, maybe I go too fast. When you get A ds equal to V dV, you rearrange, you get AT equal to V dV ds. After that, what you do, you pull this equation, substitute AT inside here. So you have Ft equal to m v dv over ds. Then you rearrange, you pull your ds in this equation, ds, because you substitute this equation inside here, you pull your ds to the left hand side. Then you do integration. When you you get this equation, yeah. When you substitute the equation in here, you get this one. Force ds equal to mv dv. I hope you see how you get this equation, yeah. You get this equation with the help of a ds equal to v dv equation that you learn in chapter 1. Okay, because we want to simplify this equation, we want to take out the AT. We don't want to see our calculation in AT. You want to see in the term of velocity and displacement. Okay, we can change this equation in acceleration mode into displacement and velocity. Okay, because most of the instrument out there, you can measure distance, you can measure the speed, but there's no instrument out there. You didn't see in your car, you'll see acceleration gauge there, right? So these are the two convenient parameters that we can measure: displacement and velocity. Okay. So next, I will continue with the mathematics steps. I have ds one side, dv one side. Next step is to do the integration, because once you have the ds and dv one side, next you carry out the integration. Okay, you integrate left hand side by looking at the displacement or position from position 1 to position 2, ds, and on the right hand side you're integrating the velocity. So velocity at point 1 to velocity at point 2. You get the second equation here. Okay. Next, you continue calculate for right hand side. Left hand side you remain first. You continue to develop the right hand side. So when you integrate, again you need to recall the integration skill here. When you integrate m v dv, m is the constant. If you're lazy, you can always pull the constant outside first and then you do the integration. It's like integrate x dx. You integrate x dx. What you do, the exponential of x, you plus 1, pull the end result, divide by the end result. So means this is x dx. You get the result will get x power 1 minus 1, you get 2 divided by 2. So if you use the same concept, m is a constant, you can move outside. V, you integrate dv, you get v squared divided by 2. And then you pull the m inside back. You get 1 over 2 mv squared, the second point, minus half mv squared, first point. So this is an integration products from here to here. It's mathematics steps. It's nothing deal with engineering or dynamics. It doesn't link with this module. It's a common mathematics procedure. Integration procedure become this one. Okay. Next, from the diagram, we have done with the right hand side. Now we focus on Ft. So if this object moves in the curvilinear motion, and we know that this object is having an external force in the resultant direction. So once you have a force in different direction from the movement direction, they will form a theta. So from this theta, when you draw free body diagram, you can form a triangular, a right angle triangular that allow you to use trigonometry to project this force into normal and tangent direction force. So basically, this force is over here. I hope you can see. So this force, you can bring it to here. You form a vector diagram. Okay, but we are interested more in tangent now, tangent direction. So your force in tangent direction, you can write in the force cos theta. Why? Side and hypotenuse. This is 90 degree. This is your angle. What is cos? Cos is side divided by hypotenuse. So you get in tangent, force in tangent equal to force cos theta. You substitute inside there. Okay. Before we move forward, remember what is the fundamental pattern of the work. Work is force multiplied by R. This is when this equation is when your object moves in the curvilinear form. We will use this integration f dot dr when your object moves in the curvilinear pattern that we already explained in the earlier session. Okay. So what we do, and also we convert the force and the R into ds. Apologize, typo error here again. When you ds, this one should change to s. A typo error in my slides again. This one is not r, but it should be s1 to s2 because you're already integrating your ds, no longer r anymore. Okay, typo error. So when you recall this equation that you learned in previously and compare with this equation, okay, so you substitute this one inside here. You substitute ft equal to force cos theta, this component inside here. You get integration of force cos theta ds. Do you see the pattern? When you substitute this one in, you see this one. This one equal to work from one place to another place. That's why left hand side, at the end, you get this form. You work from one location to another location, 1 to 2, equal to the previous calculation that you derive. You just copy. This is the, I think it's a new equation that you learn in the second session for today. This equation we call principle of work and energy for particles. This equation is called principle of work and energy. This equation. Work done when one particle travels from point 1 to point 2 in the curved linear motion equal to 1 over 2 mv square minus 1 over 2 mv square. Now rethink what you learned, recall what you learned in your statics chapter. You have three kinds of energy, but later I just bring up a little bit when we learn about energy. Recall what you learned in statics. You learn about three types of energy: kinetic energy, potential energy, what else? Spring energy, and so on. Right? But the most main you learn in statics is kinetic energy and potential energy. So you see the form of kinetic energy over here. 1 over 2 mv square is a kinetic energy. 0.2 minus 0.1 means you take the energy, kinetic energy at 0.2 minus kinetic energy at 0.1. Okay, so this equation also tell you work done to travel, work done from point 1 to point 2 is equal to the differences of energy from one point to another point. The end point energy at the endpoint minus kinetic at the initial point, also equal to work. That's why this is called principle of work and energy. Inside here, you see energy and work. That's why the name come like that. Okay, work on the left hand side, energy at the right hand side. Okay. So this is what I mentioned just now. mv square is a kinetic energy. So for this module, we use T, capital T, to represent kinetic energy. So in short form, you can write work from point 1 to point 2 equal to kinetic energy 2 T2 minus T1. Because later we will still use kinetic energy again and again. It's a very lengthy equation, so we just simplify. To simplify kinetic energy equation, T2. T2 equal to half mv squared. Or T, when you see T and it represents kinetic energy, always recall equal to half mv squared. Okay. One note here, or is a good news for everyone. Kinetic energy always is a positive magnitude, or is always a positive energy. So energy here, T energy always is a positive value. Okay, it doesn't look where is the direction. If you talk about energy, you either take it out, or energy you cannot destroy, like the conservation of energy. You cannot destroy or create an energy, right? It can only change form from one form of energy, for example, kinetic, to potential, to mechanical, or to chemical energy, or to thermal energy, and so on. Okay. Again, is a good news. Energy always positive. Magnitude, I mean the value for the energy always positive. Okay, so this one already explained just now. 2 and 1. Final minus the initial. Okay. So here we explain the derivation of work and energy. Yeah? This equation link you between work and energy. So it also gives you an opportunity to look at the question. If the question gives you velocity, you can use kinetic energy equation to solve for the work done by the object itself. Okay, if you look at the equation itself, kinetic energy equal to mv squared. As long as there's a question that gives you velocity at one point to another point, you can calculate work. Okay, so this section, it can continue from the previous question that I asked you in chapter 1, when you use the equation of motion to calculate velocity. Okay, it can continue one more subsection, ask you to calculate work done by that particular object. Because previous chapter, you can able to analyze the initial velocity normally will be given. You can use the equation of motion to calculate the V at the last position, or V2, provided you have a constant acceleration. Provided you have a constant acceleration, you have 3 equations of motion you can use. V equal to U plus AT, or V equal to V naught equal to AT, half AT. V square equal to something, S equal to something. There are 3 equations you can use. Okay, this equation, it can extend to a system. Okay, it can extend to a system. For example, a liquid. You can calculate the sum of work done by the liquid, right? By given this equation, by using this equation, or you add the sum shape, the sum symbol in front of the T2 and T1, and you rearrange, where you pull the minus T2 from the right hand side into right hand side, you get a positive sign. That's why there's a positive sign here. This equation is popular when you involve kinetic energy, work, and kinetic energy at point number 2. This is initial, this is the work done, this is the last energy you have at the station number 2, or your end position. Okay, so are you able to explain this equation and this equation, the meaning? If you look at this equation, U equal to T2 minus T1, what does it mean? The total work done on the system, or on the particles, or by the particles, equal the change of kinetic energy you have. And you rearrange again. If you put in this term, what does it mean? It means kinetic energy at initial point, or at the point of your studies, your starting point, plus the work done on the particles or by the particles, equal the final kinetic energy at the second point. Okay, basically we derive this one from this equation. Same meaning, same meaning. Okay, we have done with the principle of work and energy. Now we look at friction. Okay, now we start to look at friction. Friction also can do work, as long as you recall what is the definition of work. How work is done when the force and displacement in the same direction, you create force. You create work. So same with friction. Friction also one kind of the force. So if the friction go along displacement, it also create force. All right. So let's say you have a force object sliding from the distance here to here. You have a S, same constant velocity, but you pull the object from one point to another point over a rough surfaces. Okay. Okay. Then we turn this object, this behavior or this motion into free body diagram like this. Okay. How do you draw the free body diagram? Draw the object. First point or first force you draw in your object is the weight always pointing down. But of course, you know that you can always move your force at the same axis line, right? So you can either draw your weight pointing down, or you move your weight going up a little bit just to give room to other notation or other label. It's the same. Weight you can draw at here, or you can pull it up a little bit, pointing at along the same axis. Right? So you have the weight, first force. Second is the pulling force, P, on the object. And they always, when there's a contact, again, for this module, when there's a contact of surface between the object and the surface, they always a normal force. Don't forget about this component. Okay, when it comes to test or exam, this component always missing in the answer. All right, when there's a contact object with the surface, they always are normal forces. And the purpose, one of the purpose of normal forces is to calculate friction force. Friction force equal to friction coefficient times the normal force. We have seen this equation in chapter 2 and even chapter 1 when we consider friction force in our calculation. Okay, now only we look it a little bit deeper on how friction create work. Okay, you should be familiar with this friction already. Friction always opposite of the motion. The object is going this way, so the force is always opposite of the motion. Any question on the free body diagram? Everyone good?
Yes.
All right. So from the free body diagram and the kinetic equation just now, this one, principle of work, principle of work or energy. You can write this one or you can write this one, but from this point onward, we will use this form. Kinetic energy before plus work done equal to kinetic after. We will use this format. Kinetic done before the accident happened or before the incident happened. Kinetic plus work done equal to kinetic after the event. So here, we use this free body diagram to build the energy and work equation. Work done before, kinetic energy before plus the work done, this one is, plus the work done equal to work after. Okay, so let me see if I add anything. Okay, so this is the equation that we will use to solve all the question. Yeah, so you will see maybe, yeah, so this is the form that we use, the equation we use when we come to friction force. Right, friction force, this is energy, this is the force, this is the friction, what else, equal to mv square. Right, but anyway, this is tell you that how this equation can be balanced. Okay, how equation can be balanced. From here, we know that the P will equal to the friction force. This force magnitude will equal to this one. This is, we already learned already. The friction will always say, the friction magnitude was same as a pulling force when the object continue to move. Okay, when the object continue to move. Okay, the force will always same as this one, right? Let's look at one example, and then we call it a day. Example number 2, you're given an object sliding on a path, and this path was having a 10-degree slanting angle. The distance from this position to this position labeled as S, coming in the velocity 6 meters per second. You read the statement. You are given the mass of the automobile. The car is not weight, but have a mass of 1750 kilogram. Travel down 10 degree angle, incline road at a speed of 6 meters per second, which is agree with the diagram. It give you the scenario already. If the driver jam the brakes, means at this point is pressing on the brakes, what happened to the wheel? The wheel will lock and it will slide along the distance here, causing the wheel to lock. Determine how far the S will travel until the skid on the road. The coefficient kinetic friction between the wheel is given. Okay. Okay. So in this case, it assumed that the car will stop at this point. Means you need to use equation. You assume that the car will stop at here. Means velocity at this point is 0. Try to look at the question. The question asks you to solve S. You can use the equation that we learned previously, or you can use the equation of energy and work to solve this kind of question. In this example, we use the principle of work and energy to solve it. If you use the previous chapter, the one that we learned, same one with the equation of motion, you still get the same answer. All right. So we draw a free body diagram. I couldn't find the same shape of the car, so I just use a sport car here. So I draw the axis. So this is at the speed of 6 meters per second, and the middle at that middle point, and then at the stopping point S here. So the distance from the driver step on the brake, start to jam, the brake start to the wheel start to jam, and this one I assume the cars come to stop. Then I put in 10 degrees C in my free body diagram. Draw the axis, free body diagram. The first force, as you can observe through my lecture series, when I draw free body diagram, first force I put into my free body diagram always the weight, because that is the most easiest force that I can determine. It always pointing down on the earth. So W equal to mg pointing down. Of course, I can draw this weight over here. No issue. My weight I can always draw here. But you know that when you have a contact of surface, you always need to recall when there's a contact between something and the surface, there's a normal force in the free body diagram. So I don't want to overlap my weight here when I prepare the slides. Of course, in your free body diagram in your exam, you can draw arrow, the weight and the normal force. Try to have a distance, so I know there are two forces in your free body diagram. Okay, so when you draw the normal force, remember normal force always perpendicular to the plane. Normal force always perpendicular 90 degree to the surface. Oh, let's say this is your surface. Your normal force always 90 degree to the surface. No matter how it's slant, it's always 90 degree. Okay, even it go like this, the normal force will go 90 degree. So this is the behavior or trend of your normal force. Always 90 degree to the surface. And then you know that from this point, you jam the brakes, the friction, the car will go this direction. So the force of your friction force go another direction just to stop the car. Okay, what else? Mu is given. Mu, the friction coefficient is given. Mass is given because I try to clear my board over here. I just pull all the information here and I focus on my diagram. V is given. Right now, my intention is to clear my board here so that I have more space to use. Any question on the free body diagram? Anything that you don't understand or you don't know how to draw? Okay. All right. Yeah, this is just an extra question I asked you. This is you can take as your homework or revision, right? Okay. Okay, so you know that when you have a force in normal to the displacement, this one don't generate work, because this component perpendicular 90 degree to the displacement, this yellow arrow, normal force, do not generate work. So you don't need to consider this one. But the gravitational force, yes, you need to expand this force pointing down and moving forward like that. So again, weight, you also have two components. One is moving down with its 90 degree to the displacement. So the component that going down doesn't do work, but there's one component of the weight that is going this direction is doing work. Okay, so the weight component that going this direction is same as your displacement direction. So this one will give you positive work. What about friction? Friction go against a displacement. Friction work will be negative. Yeah. Okay, so this explain about that one. So we just apply the equation. All the force in normal direction equals 0 because F equal to ma. F equal to ma, we look at normal direction. This is the normal direction. There's no acceleration in normal direction. If there is an acceleration, then the car will be flying. But in this case, the car stick to the sliding plane. So F equal to ma, there's no acceleration in the normal direction, 0. On the left-hand side, you only need to solve the free body diagram. In normal direction, you have Na, you have weight this direction. When you expand this resultant force here, you have one direction here, one direction here. So the one is pointing down is negative, so that's why you get negative mg cos theta equals 0. From here, you find your Na. Homework, you substitute the value of degree, 10 degree, G, you know how much, 9.81. Mass is given. Okay, mass is given. So you substitute, you get one answer for your Na. Once you find your Na, you can find your friction force. Na equal to this number. But anyway, in exam, all this value will change. So this is just a guidance for you for this example number 2. So from once you get your Na, you get the friction force. F equal to friction coefficient times the Na. Okay, this one. Friction coefficient 0.5 multiplied by this number, you get the friction force. Then you apply the work principle, right? Principle of work. So principle of work and energy, kinetic before plus work done equal to kinetic after. So kinetic energy half mv square, kinetic energy equal to half mv square sub 1 means before the incident happened. What is the work done? You have two work here. One is the work done by the gravity. Mg sine, mgs sine. Okay, or you can move sine to the mg also can. Right, both same as long as your force and displacement same direction, they will generate force. Why now your force, your work done by gravity is positive? Why now your gravity is positive? Look at the object motion. Where is this object going? Going down. This object going down. That's why your your y axis is positive going down. your work done is positive going down because the object is going down. Yeah? Take note on this one. Huh? Take note in your revision note there. mg in this case, the work done by the gravity or your W is positive in this case because the object is moving from high ground to low ground, which is your y is positive going down. Okay, positive mg sine theta. The friction force also have done work, but why negative? Because the friction force is opposite of the displacement direction. Okay, again, the force, displacement, when the same direction, you get positive work. When the force is opposite with the displacement, you get negative work. That's why you get a negative friction force times the displacement. Force times displacement, you get work. But why negative? Because your force is opposite of the object, of the movement direction. Equal kinetic energy at the second point, which is half mv squared v2. From here, you have all the parameter already. You have the mass. You have velocity at point 1, which is here. You have the mass. You have the gravity. You have the displacement. You have the angle. You have the force of the friction. You found it already. You have the displacement. You have the what else? Huh? Oh, okay. You want to find the S, right? The displacement here. You don't know how far it will slide. So there's one unknown here. You have the M here. You have the V here. V2 is 0 because it stopped at this distance. V2 is 0. Okay, homework. You substitute all the value. This is your reference answer. S, you will get 5.76 meter. Important that you should understand the strategy we use and what is the reason why we use work and energy principle to solve this question. Because for work and energy equation, you only involve velocity, work done, and velocity. So here you have the M, you have the force and the displacement. The question asks you the displacement. It do not ask you about time. Be careful. If the question asks you about time, then you need to go back to chapter 1 section where you need to use the Newton equation. U equal to U naught plus half AT square, or V square equal to U minus 2AS, and so on, right? So be careful. This question do not ask about time. This question asks about displacement, S. And displacement is one of the component you calculate work. Again, what is work before we go for today? What is work? Work is produced or is done when your force and displacement, they go in the same direction. You get a positive work. When your force and displacement opposite direction, you get a negative work. When your force and displacement, they are 90 degrees to each other. If your force is 90 degrees, there's no work done. For example, the normal force on the displacement axis. No work done by any. We have done using the equation of energy. I show you another way where you learn in your chapter 1. You use equation of motion to solve. Same question, different method. Okay, so this question can be manipulated or can be modified into chapter 3 question, or it can be modified into chapter 1 question. Both get the same answer. You use F equal to ma. So force in the free body diagram equal to left hand side, mg sine theta equal to friction force, equal to ma s direction. A, you already find equal to minus. So from here, this equation, you have M, you have G, you have theta, you have friction force. M you have, so inside this equation, A is missing. A you find is minus 3 point something. Then you use this equation. I mentioned just now you got 3 equation of motion you can use. This is the second equation of the 3. You use V2 equal to V naught square plus 2AC and the change of displacement. These 3 equation of motion only works when you have a constant acceleration. Only you can use this equation. You have the final velocity, you have the initial velocity, you have the acceleration that you calculate from F equal to ma. You only left out the distance travel. So S minus S initial, this one is 0 because we take as starting point, so 0. You only left out S. So I substitute the value here. 0 equal to 6 square plus 2. A you find just now, only one S is missing. You get same answer, S equal to 5.76 meter. Same question, different approach, you get the same answer. Okay? It depends on how question asks you. Okay? The question can give you hints. Section A, use equation of motion to solve. Section B, use principle of energy and work to solve. Okay? Or it asks you, verify your answer in section A by use section A, you use equation of motion F equal to ma to solve. And the second session, it might ask you, verify your answer in A by using principle of work and energy, which is the previous slides here. Verify your answer A and B. One method, verify one method. Okay. Okay, I think we stop here. Let me stop the recording.